So let's see. We've got one way to determine if two things are similar is if they have all the same angle lengths, angle measures. So you guys have drawn a triangle. I'm going to draw a triangle too. Just to be different, I'm going to make it not equilateral. Can you guys draw another triangle that, without using a protractor or whatever, that has the same angle measures roughly, but is not the same, but is not congruent to this? Whatever triangle you just drew, I want you to try another triangle, try to draw another triangle, has roughly the same angle measures you in your first one, but is not congruent to your first one. So obviously, what's got to happen? What's got to change for it to not be congruent? Sides have to be different lengths, but in order to preserve the angle measures, I basically, oh, that's horrible, Jeff. I basically, let's just make it a little bit. There we go. That's roughly good. You can tell it's not perfect, but it's okay. What would have to be true about the sides? Okay, they're not equal, for damn sure. Yes? But what would have to be true about them? What have we effectively done to this triangle? Yes?
Reduce the dilation, is that the word?
Ooh, excuse me. We talk about scaling up, scaling down, enlargement, reduction. I feel like that's the idea you're talking about. So for example, if this side length is 3 and this side length is 6, and this side length is 5, how long must this side be here? So those two are similar. They have all the same angle measures. What do you guys think must be true about that side in the second triangle? This is related to what you just said, right? Say it again. 10, yes. So all a similar triangle is, and we're going to get into the various ways to tell if two triangles are similar, but all they really are, every single one of them is just, if you start with a triangle, blow it up or shrink it down. So it's kind of like I've multiplied all the sides by something. If I want to shrink it down, I multiply them all by some fraction less than 1. Yes? You guys have all heard of like architects. What's if the architect is going to come in and they're going to propose some building to somebody? What are they going to bring in? A model, a scale model, correct? So everything is going to be maybe 1/60th the actual size, so it can actually fit into the room. Yes? You guys got okay? So that's all the similar triangles are built on, is this idea of one is a multiple of the other. Yeah, I love it. And this is normally something you're kind of used to, this idea of what makes things similar. So just to kind of make this a little more formal. So if I have triangle ABC, and I have another triangle XYZ, these will be similar if AB is equal to XY, well, AB divided by, let's say BC is equal to XY divided by YZ. All right, let's think about that for a minute. Actually, let me set this up a little different way. That's getting a little ahead of myself. If I do AB divided by XY, and that is equal to BC divided by YZ. That's better. Oh yeah, two things, sorry. So if I take, this is sort of like what we applied up here. You guys did 6 divided by 3 is 2. Therefore, this divided by 5 must also be 2, so therefore that must be 10. So that's the basic idea behind similar triangles.
So if I find out what multiple was used, I just apply that multiple to whatever else I don't know. For similar triangles, what must always remain the same between the two? Obviously, the side lengths can be different. Angles must remain exactly the same. So are two congruent triangles similar?
Yes, they have to be. They must be. All it takes to be similar is you have all the same angle lengths. And if I'm congruent, I also have all the same side lengths. So two congruent triangles are a specific type of a pair of similar triangles. Nothing major there.
So, and this would also be, so I must be able to make a one-to-one correspondence between sides. This side corresponds to this side corresponds to this side. Then I can kind of finish this out. This side must correspond to this side. So I know this might be the first time you've seen like a three-stage equality statement.
You probably run into this somewhere before, but that's just saying that ratio is the same across. It's just, if I triple one side, triple another side, I have to triple the last side to kind of blow that triangle up. That's all that's really saying. Now behind all this, what would I have to be told to know these were similar before I can assume this, of course, is all the angles. I must have, for example, in this case, I'm assuming angle A. The measure of angle A equals the measure of angle X. The measure of angle B equals the measure of angle Y, and the measure of angle C equals the measure of angle Z. Now, you guys know, you've used this book before. You know they're going to give you triangles where one of them's kind of like rotated from the other one. So you have to first identify which angle corresponds to which angle in the other triangle. Yes?
Have you guys ever seen those Russian nesting dolls?
Do you know what I mean when I say Russian nesting doll?
Yeah.
They're kind of, my mom had a set of them when I was really young, and I was fascinated by them. So that there's kind of a big one, and then this is horrific to us, so you tear off the top of her, and there's another one of her inside. Exactly the same as the outside, just smaller scale, yes? So those are examples of similar shapes that are beyond triangles. So, on that note, you know that we're going to talk about similar trapezoids, similar whatever. They don't just have to be triangles. But we're going to kind of focus primarily on similar triangles.
So let me give you an example. Let's say, all right, let's say I've got A, B, C, and then I've got Z, X, Y. And I'll tell you that angle A is congruent to angle X. Angle B, let me just use the sign, is congruent to angle Y, and angle C is congruent to angle Z.
Just take a moment, and can anyone, don't say anything out loud, bless you. Can anyone determine a pair of sides, one from each triangle, that are a ratio that would show you how much bigger one triangle is than the other? Sort of like I did a minute ago with
These, where I can make a ratio. Yes? So can you guys identify which sides are similar? And I'll show you a better way to write this, by the way. Can somebody give me two sides that would be involved? So one thing I can do for myself, let me do this for you. Angle A is congruent to angle X. Angle B is congruent to angle Y. And angle C is congruent to angle Z. You guys have seen those kind of markings before? I mean, if I just do one, that's our normal angle thing, but now I can kind of keep track of which angle goes with which angle. So that tells me where the nulls are, and that tells me which sides should be similar to the other sides. Is everybody with me? Is anybody with me? Thank you. Okay. And again, because they're gonna rotate these damn things, and that's the worst thing for students. Even if they progress through the Healy levels, you're still gonna have a little trouble when things aren't the same orientation. But once you've drawn those in, can anyone tell me what should go underneath side AB to start setting up a similarity set of ratios, like I did just a minute ago? Yeah, YXY. Because you got this angle's the same and this angle's the same. So AB. Let me do it like this. I think you guys have maybe seen this before. AB to XY. I'm pretty sure last semester we talked about ratios a little bit, but that's just showing a ratio. AB is to XY as what? Somebody else give me another set. AB is to XY as BC, good, because you start 2, 3, right? BC 2, 3 is to YZ, kick ass. So the basic idea of similarity is really, really simple. It's really simple. You take a triangle and you blow it up. You zoom in on it, right? How do I determine that factor that I multiply by to zoom in on it is to divide one side to another, but I have to pick the sides that are similar. So another way to look at the sides that are similar is what angle is AB across from? C, it's got 3, right? So then the side across from the 111 must be similar to that side. Must be in a ratio with that side. Okay, I like it. Just trying to get you guys ready, because you're gonna have all these problems where they're kind of turning around. You're gonna have problems here we're gonna look at in a minute where the triangles we're working with both live in a bigger triangle. So that can get a little tricky to keep track of what the hell's going on. So let's do this. The same way we did with congruence. Let's start listing some general requirements to be similar. The most basic one. Is the one I think you guys told me earlier, which is angle, angle, angle. And to be really honest, that's kind of like a definition of similar triangles, is all the angles are the same. Why is that not good enough to be congruent? Why is that not like SAS is congruent? Why is AAA not good enough to be congruent? Sides could be different. Okay, I like it. Now, real quick, let me ask you this. This by itself, this is kind of stupid. This is kind of silly. All right. If I tell you that one triangle has a 50-degree angle and an 80-degree angle, is that cool? And I tell you another triangle has a 50-degree angle and an 80-degree angle. Some other triangle has a 50 and an 80. Are those similar triangles? Hell yeah, why? Yeah, so it's kind of simple. I don't need somebody to tell me all 3 angles are the same. If they just tell me 2 of them, the last one's got to be the same, because both triangles add up to be 180 degree measure. I like beautiful. So all I really need is love, but that's okay. All I really need is two angles to be congruent, and then I have two similar triangles. So if I know this, we're obviously totally cool. If I know this, we're still totally cool because it means the first one. Kick ass. And then we have, oh, being silly. Let me make sure I didn't miss anybody. Oh, I did, sort of. Let's do this last dude. And this one's going to seem a little interesting. We have one, it's SAS. Now that's shown up before, correct? Let me see if I can give you, yeah, let me give you, yeah, this one's more, let me kind of break this down for you. So let's say I've got, let me do this on the next page. If I've got this little tiny triangle dude, and I've got this larger triangle dude, and I know that angle B and angle Y are congruent. And I know that AB 2XY is the same thing as BC 2YZ. Oh no. I'll be all right. I've got it back up. Hopefully I got it back up. Yes. So this is a little different. For congruence, the sides had to be equal to each other and the angle between had to be equal. SAS for similarity means the angles have to be congruent, but the sides have to be in this kind of ratio. Okay. I haven't used these in a while. These are powerful. Holy crap. So it doesn't mean, so side angle side for congruence meant two sides had to be equal to each other and the angle between had to be the same. For similarity, the angle has to be equal, but the sides just have to match up in a ratio. So AB blown up is XY. BC blown up is YZ. Now, do you see why this works? If we know that AB is multiplied by the same thing to get XY as BC is multiplied to get YZ, why necessarily would this lead to them being similar? What's the most basic way to tell that two triangles are similar? What's almost a definition of similarity? All the angles have to be equal. Yes? So, why does this work? So if this side and this side in a ratio are the same as this side and that side in a ratio, that pretty much says this side and that side have to be the same. Also, the angle is kind of open the same. So to be really honest, this is a very interesting idea of, if I start with an angle, I would make this triangle here if I stopped there. If I kept going for a little bit, I would actually make this triangle. So this is a broader idea of, like, if I have a triangle and I draw a line parallel to the base, that's that AC line, I've now constructed a little triangle that is congruent to that. Okay, somebody with me so far?
I know today's lesson so far has been exciting stuff. This is really cool. Can anyone tell me, what did I just say about AC and XZ? What must be true about them? They are parallel. Which means, what's this thing here called? Oh, you're drawing big enough, Jeff, you can see. What's this line here called? These two are parallel lines. This is a transversal, kick ass. The most fundamental thing we need to be true for two triangles to be similar is all their angles must be equivalent. So any other method to tell that two triangles are similar must result in that. So all I know is this angle is the same. And I know that these sides are kind of like the same multiple of each other. If these are then parallel, whatever angle this is, how must it relate to this angle? They have to be congruent because transversal and corresponding angles, yes? And then the same thing over here. Okay. So it's a little bit evil. You gotta be really careful. Side angle side for similarity is not the same as side angle side for congruence. Side angle side for similarity just means the ratio I can make between two sides is the same as the ratio I can make between two other sides, and the angle between them is the same. So it's a little looser. The whole idea of similarity is definitely looser than congruence. Bum, bum, bum. If you, so here's one application of this. Have you guys ever seen the people that are out there? They have these things, they're normally like yellow, these little dudes that they're kind of looking through. Right, they're surveyors. I've seen them on Gross One every now and again. Do you guys know what those surveyors are doing? They have this thing, it's on a tripod, and they're kind of looking through it, and they're taking notes, and they're looking through it. And normally there's another team further away that's holding a stick or something. Do you guys know what they're doing? Nobody knows. Okay.
I think they're checking we do that at work, to find a level.
Yeah.
Like level off to be able to know how much there's like a speed in the land to see how much more.
I love it. So they can tell how different the heights are between the 2 points. They can tell all kinds of angles between the 2 points. Fundamentally, what they're doing is they're making sure that there's not been some like major sinkage or changes in elevation, because that could lead to structural problems, right? So you see them out there. My little brother shadowed some surveyors, and he says, now I understand trigonometry. We're not going to only do trigonometry, but that's a huge part of what they do. So let me ask you this. If there was a tree or something, let's say, or the tower, you guys have seen the tower out there by the student center, right? Outside the cafeteria and all that stuff, there's the tower. At night, if you're here at night, it changes colors, the top of it. If you've never been here late, it does. Take my word for it. Does anybody know what I'm talking about? You guys are looking at me like I'm crazy, which I'm used to. And I want to know how tall this thing is. And I'm standing here. And let's say let's just pretend I am somebody else. I'm 6 foot tall. There's also this device that can measure the angle. So if you look straight and you look up and you see the top of something, it'll measure the angle between there. So let's say that I know I want to know how tall this thing is. So I've got this little triangle here that has 6 feet on one side, and I can measure how far this is. And I want to know how tall this thing is. So if I know how tall I am, I know how far away from the base I am, and I know how far this is. I've got this little triangle and this big triangle that are congruent.
then the height of the tower would be some multiple of my height. So where do you get the idea there? That's one quick application of similar triangles in the real world. I could actually walk off the distance for the little triangle. I could walk off the distance to the tower. I don't have to climb the tower, thank the gods. Now, you could use trigonometry, but you don't need to. All I need to use are similar triangles. So the two triangles that are similar are the one triangle that I make, that little dude, and then the one triangle that goes to the tower. Those two are similar for the exact same reason these two were. Because here I'm kind of acting as the parallel line to the tower. Okay, maybe. Oh my God, these things are so powerful. Oh yeah, we already did that. Cool. So, let me see. Here's a real life example of what I'm talking about, real quick. There's something called Devil's Tower. Have you guys ever heard of it? It's this, I think it's in Wyoming. It's this huge geological structure, right? And I love to go hiking and such. I haven't been to Devil's Tower yet. I'm not gonna climb it. One time somebody parachuted to Devil's Tower and they had set up a rappelling rope to come back down, and when they landed, the rappelling rope fell off and fell to the ground. And he was stranded there for a week until some other people could come from across the country. This is like way back. I can't remember how long ago. It's like around 100 years or so. And they had to have this team come out and then climb it and then save it. So, and you don't have to know any of that to make the math make sense, but it's just a neat thing about Devil's Tower. So let's say that we measured this off. We measure this angle, we measure that angle, we measure the distance here between them, and then I could create a set of similar triangles. So this whole triangle would be similar to this triangle here. And if I could just figure out what this height is, I could then figure out what that height is. So I could potentially set up either a little platform, or I could just have somebody standing here or something, and I could actually set up two similar triangles and figure out how tall that thing is without having to actually climb it. So these are just little things that happen in the real world. If you ever wondered how they figured out how tall something was, how wide a lake was, because you could do something similar with the width of a lake. I don't know if I have that with me, probably not. No, okay. Here, let's do an actual problem together. Can you guys, first off, a nice thing you can do for yourself. First thing I want to ask you is, do you know anything about any other triangle besides that 40-degree one that I gave you? Any other angle in the triangles besides the 40 degrees? So those are the same, which is good. Are there any other angles you know anything about? Not the measure, just anything. There are two angles that I know are equal in measure.
See,
Yeah, be more specific.
the insides of the triangle.
Yeah, so BCA has to be congruent to ECD, for example, yeah?
Yeah,
Why?
because it's the tangent rule, but
It's kind of neat. I like this because what letter does this make? And they're vertex angles. Yeah. So vertex angles are just two that are kind of like opposite of each other when two lines kind of intersect. It kind of makes sense that they have to be the same size because they're made the same way. So as I open my arms up, this angle's getting bigger and smaller, the same amount as over here. Okay. So what does that mean then about the two triangles? This angle, these angles are similar, are congruent. These angles here are congruent. We don't know how big they are, but who cares? What does that mean about the two triangles that I'm working with that kind of meet at their nose right there? What's true about those two triangles? They must be similar. Can you guys take a moment? Here. So those must be equal because of the fact that they have to add up to be 180 degrees, correct? Can you guys take a minute and set up any ratio you see? A correct ratio showing which side is similar to which side. Preferably a side that we are interested in or know something about. So for example, side BC for this problem, I don't care about it. So if I take, for example, what side did somebody start with from this triangle here? Anybody pick a side to start with? Which one? BA. Okay, so BA is to what? And I'm going to see ED just to be really pedantic. Okay. So everybody see where that came from? So when I'm making this ratio, I really could set up a proportion using sides from the same triangle equal to sides from the same triangle. We'll talk about that mathematically in a second, but it's kind of nice to go, this side is related to this side from the other triangle. What's another ratio I could set up that actually involves? So BA and ED are good because I actually know how long those sides are. And then what's the one that's related to what I actually want to know? What side from the smaller triangle? AC must be related to DC. Yeah? AC to DC. Kick ass. Alright, so this, a lot of the time the idea is kind of like hidden under the notation you have to use. Do you guys agree with that? In mathematics, a lot of the time the idea is simpler than the notation allows. Hopefully this isn't that insane. And I'm being a little bit more careful than normal just because I want you to get used to really highlighting what's the same. So like BA is the same as ED. Can you guys fill in the numbers in the variable and try to solve that? I want you to figure out what X is. And I will go back and say, yeah, I did say we do this together. But I'm an evil math teacher. Here. Of course, BA is 6. And then ED is 8. And then AC is 7. And then CD is what I don't know, the DC. Do you guys remember how to solve that? This is from, algebra. This is also from last semester. Yeah, cross multiply. And cross multiplication, real quick, is the thing that people want to do more often than you can. The only time you can efficiently use it directly is if I have a fraction equals a fraction. That's the only time it works. And then it's a shortcut. Bless you. Does anyone know why cross multiplication works? It should feel sort of like you're cheating. All I do is I bring the x up and I bring the 8 up, right? But real quick, the reason it works is if I multiply both sides by the common denominator. The 8 dies here, so it looks like the x came up. The x dies here, so it looks like the 8 came up. So it's just a shortcut. So that leads to what? What equation? 6x equals 56. And then divide by 6. And when you get something like this, I normally just want the fraction. You don't have to make it into a decimal unless I say, round decimals to the third decimal place or something. What does that reduce to? 28 over 3?
23 over.
No. it's not. Yeah. Okay. So this is a decent little problem. It's not horrible, especially when you remember, you don't have to remember the name of these things. You don't have to remember the name of vertex angles. But you do have to remember that these are congruent. Okay. Yeah, okay. I don't want to do these. What I want to do, yeah, let's do this one. This one's definitely tricky. This is the one I was talking about where you have triangles that are inside of a larger triangle. How many triangles are there?
3.
Good, I love it. There's the big ass one, the blue one, and the green one. Yeah? So the blue and the green together make this big ass one. Can you guys, okay. Let's look between the green and the blue for a moment. The green and the blue separately. Doesn't the blue have the same side as the green? They both have this side. Okay. So they have a side going on. This angle and this angle are the same, correct? But do they have anything else that I'm still missing something to tell if the blue and the green are congruent, right? Well, let's see. These two angles have to do what? Let me call this one, I'm going to call this one little a, I'm going to call this one little b. Those two angles have to, good, they have to add to be 90. I think that's what you said. And, all right, somebody with me so far? That whole angle C is 90, so the two angles that go into making it must add to be 90. What must be true about, probably should have named these something different, but that's okay. What must be true about angle big A and angle little a? Everybody focus on the blue triangle. As soon as it focuses itself. Come back to us. Alright. The blue triangle. You got angle little a, angle big A, and a 90-degree angle, correct? What must angle little a and angle big A, what must they do together? They must add to 90. Is that cool? Okay. If angle A plus angle B make 90, and angle little a plus angle big A is 90, what must be true about angle little b and angle big A? They must be equal to each other. So now we know angle little b equals angle big A. We know that angle ADC equals angle BDC. We knew that from the beginning, right? Because that's 90, that must also be 90 to make this nice straight line. So I know that this angle is the same as, where'd it go? Sorry. This angle is the same as that angle. These two angles are the same. Yes? So let me see. Let's do this. So I know that angle big A is equal to angle little b. Angle big A is equal to angle little b. I know that this angle is the same as that angle. So do you see how if how do I say this? If I took this triangle and just rotated it down, the blue one would be this one blown up. You guys see that? If I rotate this triangle, here, let me do it. If I rotate the green triangle, it's the same as the blue triangle. So this angle and this angle. This angle and this angle. I like it. And this side is the same. Okay. Come back to me. In fact, since two angles are the same, then the third angle must be the same, correct? So angle A equals angle little b. And this angle equals that angle. So then what must angle big B equal? Little a. So now we've established that the green triangle and the blue triangle are similar to each other. Here's where things get weird though. It might have been weird already. The rotation isn't extreme, but it's still a rotation, so it's kind of hard to keep this in your head. So I would try to identify which sides go in the ratio. So what side of the green triangle is 12 related to? Good. So again, if this guy just falls over, you with me, which is something I feel like doing. If this guy just falls over, this side and this side would line up in terms of similarity. This angle and this angle, this angle and this angle. So this side is similar to this side. It's going to be in a ratio. Which is good, because that's the thing I'm trying to figure out. Can somebody tell me any other pair of sides that would kind of like complete that proportion? And the only other side I know anything about is 3. If that green triangle falls over, which side is in the same direction as 3? X. So then how would I put that? So this is green to blue, yes? Is that cool? Green to blue. So I better put green to blue. So it's the whole idea of proportion is once you write one ratio, you've established what goes on the top, what goes on the bottom. So I'm putting green measurements on the top, blue on the bottom. 3 over x. Kick ass. Now go ahead and solve that. So this doesn't come out to be too difficult. There is one little mathematical thing you got to be careful about. Some of you guys are just not going to think about it, and so you're going to get it right. So if I do x times x, and I get 12 times 3, mathematically there's two answers to that, but of course there's only one answer for this physical triangle. Mathematically it's positive and negative work. But of course, what do you get? 6. Cool. Okay. So this kind of problem to me is one of the more challenging problems because they kind of live together in this bigger triangle and their orientation is offset from each other. So it's a little difficult to keep track of what's what. So I like putting these little symbols on the angles to keep yourself straight, to kind of match them up. You could obviously rotate your book or whatever it is you're looking at, a test or a quiz or something. Most things you're not going to be able to cut unless, you know, it's your book, you can do whatever you want to, but okay, so they get a little more confusing when it's all part of one bigger picture. So what I want you guys to do is to work on this, which I did not. I think there's only 3, yeah, okay. I didn't have time to staple, but we're gonna make it. By the way, while I'm thinking about it, tomorrow is the day we're actually gonna use our compasses. If you don't have one, I've got a few you can borrow. Hmm? Yeah, you know, tomorrow in the context of the class, so Wednesday. Oh, yeah, you got yours, okay. Let me see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 16, 17, 18, 20, 21, 22. Yeah, it's a little bit long, so let's do this. That really sucks about you. Oh, that was the opposite side that came off, too. All right, it'll be. Yeah, these are pretty straightforward. So do all these problems on here, but then we're gonna kind of break it up. So do everything on this page here. That should be pretty quick. But then let's see. Yeah, do 8, 10, 11, 12, 13, 15, 17, I think. Let me make sure. Yeah. So everybody got that so far? So you don't have to do everything. 8, 10, 11, 12, 13, 15, 17. Yeah, 18, 19, 23, 18, 19, 23. Oh, let me see. Oh. 25. Oh yeah, this one gets trippy. Let's do that one together, I think. 46 and oh yeah, 52 for sure. Oh yeah, all these are pretty straightforward. So all those 50, 51, 52. All right. and that's good. We'll do this. So let's see.
By the way, I do want to apologize. I don't know if you can tell. I didn't really have a ton of time to get ready for this morning, so I'm kind of like going off of, flying off the seat of my pants, whatever the word is. So I'm a little bit behind where I want to be in terms of getting ready. I got some bare bones stuff we're doing today, so hopefully that's okay. How do I want to make groups? Are you guys, let's see. You guys, you know, like, you don't have to, Jeff. We can do this. Do you want to work by yourselves? I'm okay if you do. And then if you want to reach out to people near you, that's fine. Okay, let's do that. So let me know if you need some help, or you can reach out to people near you if you want to. If you need to borrow a calculator, I've got some, but I don't think there's anything you really need a calculator for, but we'll see.